So here is a nice IMO 1961 problem which is about the system of equation. We are given that x plus y plus z is equal to a, and x square plus y square plus z square is equal to b square, and x multiplied by y is z square. And we have to find the condition over a and b so that x, y, z are distinct positive numbers. So let's solve this problem. So I'm going to substitute. First of all, I'm going to work with this equation and substitute this value into this. So we'll get x square plus y square plus, in place of z square, I'm going to substitute its value xy equal to b square. And now we can add xy to the both side of the equation, and we'll obtain in the left hand side x plus y whole square is equal to b square plus xy. And now we can again substitute its value, which is z square, and now we can evaluate the value of b square, which is x plus y whole square minus z square, and we can just factorize this part. So we'll obtain x plus y plus z multiplied by x plus y minus z. And now we can substitute the value this. We can say that b square is equal to a multiplied by x plus y minus z. And from this step we will do a bit more manipulation. We can say b square is equal to a multiplied by x plus y plus z minus z minus z. So we can rewrite it as in this form. We just added and subtracted the same term, so we'll get b square is equal to a multiplied by x plus y plus z. We know its value, which is a, minus, we can add these two terms, will obtain 2 multiplied by z, and from here we can evaluate the value of z. So first of all we multiply a square inside the bracket and we'll obtain this, and from this equation we can simply get the value of z, which is a square minus b square divided by 2a. And since here we know that x, y and z is equal to a, and since x, y and z are positive, so this a must have to be a positive number. So we can simply say that a is greater than 0 is a necessary condition, and since z is a positive number, so a square minus b square must have to be greater than 0. So these two conditions we obtained here, and after solving this inequality we can say that a is greater than mod of b. Okay, now I'm going to substitute this z, what we obtained here, in above equations. So we can simply say that x multiplied by y is equal to z square. So after substituting the value, we'll obtain a square minus b square divided by 2a whole square. And next we can substitute in this first equation, which is x plus y plus z is equal to a. So we can say x plus y is equal to a x plus y plus, we can substitute the value of z, which is a square minus b square divided by 2a is equal to a. So we can say x plus y is equal to a minus a square minus b square divided by 2a. We can solve this and we'll get the x plus y is equal to a square plus b square divided by 2a. And now we have two equations. Let's call it a, and this one is our b. So now assume x and y are distinct positive roots of a quadratic equation. So we can construct a quadratic which is x square minus, here we will put the sum of the roots, which is nothing but the x plus y. So we can say that minus of a square plus b square divided by 2a x plus, here comes the product of roots, which is x multiplied by y, and we can say a square minus b square whole square divided by 2a whole square. And now we know that this quadratic has a positive distinct integer roots. So for satisfying this condition, we can simply say that d has to be greater than or equal to 0. So we can simply find the value of d, which is equal to b square minus 4ac. So we can simply say that a square plus b square, which is our b, upon 2a whole square minus 4. Since our a is 1, so the value of c is a square minus b square divided by 2a whole square, which is greater than 0. And after solving this, we'll obtain a to the power 4 plus b to the power 4 plus 2a square b square divided by 4a square minus 4 multiplied by a to the power 4 plus b to the power 4 minus 2a square b square divided by 4a square greater than 0. We can simply cancel this 4, and after solving this expression, we can simply say that 10 a square b square minus 3 a to the power 4 minus 3 b to the power 4 divided by 4 a to the power 4 is greater than 0. And now this implies that 10 a square b square minus 3a to the power 4 minus 3b to the power 4 is greater than 0. And now we have to factorize this term. So we can simply break this in 9a square b square plus a square b square minus 3a to the power 4 minus 3b to the power 4 greater than 0. And now we can take 3a square common, and 3b square minus a square inside the bracket. Similarly, we can take minus of b square common from the both terms, so we'll obtain 3b square minus a square inside the bracket greater than 0. And now we can simply say that 3b square minus a square multiplied by 3a square minus b square is greater than 0. And now I'm going to use the condition that we already have found, which is a is greater than mod of b and a is greater than 0. A is greater than mod of b and a is greater than 0. So what we can say, if a is greater than mod of b, then 3a square is greater than b square. So this implies that 3a square minus b square is greater than 0. So this term is our positive, so this must have to be a positive value. So we can simply say 3b square minus a square is greater than 0. After solving this, we can simply say that square root of 3b is greater than a, and this a is greater than mod of b. So this is our whole condition